Hello and welcome to my first online lesson here. It's going to be a little rough around the corners, but let's see how this works out. Today we're going to be talking about some of the basics of science. And obviously this will be relevant for any science class, but we'll try to focus a little bit on chemistry. We want to make sure that you guys understand what empirical means. We're going to differentiate observations and the different types of inferences, and we'll get a little bit into the scientific method today. And then in the next lesson, we'll review the scientific method and move on to some other ideas of science. One of the fundamental ideas of science is that it's based on empirical data. Empirical simply means observable, objective data that you gain from the natural world. Now, sometimes we experiment and sometimes we observe. You guys are used to gathering data through experiments, but it's not the end of the world if you cannot experiment. That can still be valid science. For example, if you're studying the past, you can't really experiment on the past. If you're studying astronomy, there's very few times we can experiment on the solar system. I mean, we did crash some stuff into the moon. That was pretty awesome, but can't necessarily slam black holes together. And obviously, there are certain health situations where we can only study. It would maybe be immoral to give people diseases. You know, if you're studying black lung, you can't really give people black lung, but you can go and study coal miners. So observation is definitely a very useful way, and that can still be observed through the scientific method. Now, science uses both observation and inference, and it's important to differentiate the two. We're used to the idea of observations. These are things that are observable to the senses. They should be objective. Everybody should agree on them. Everybody who sees this should notice that the rock fell to the ground. That's not really something that people are going to argue about. And that's really all facts are. Facts are simply verifiable observations that we all agree on. The interesting thing about facts is that even the idea of a scientific fact can change if the assumption behind the fact changes. So, for example, we saw certain facts that made us think that atoms were certain ways, but as we had a new technology, we realized that we were seeing things differently. The age of the Earth has been reevaluated. We have a certain age of the Earth now. That's a fact. The Earth is so old. But that could change with new data. Unlikely. There's certainly several different ways that we're honing in on the age of the Earth, but you get the point. Even Pluto's planetary designation, 7, 8 years ago, if it was a true and false quiz, if I said Pluto's a planet, you'd say true. But now you say false just because of the way that we understand the universe. An inference, though, is really where we're getting into the meat and potatoes of science, and that's the idea of trying to explain observations. So it's important to understand when you're adding value to your observation, because people could find problem with that. You can certainly say that gravitational attraction brought a rock to the ground, but people might argue with that. Maybe someone thinks that the reason that rock went to the ground is because there are invisible fairies that want nothing more than to put things on the ground. So when you let go of them, they grab them and put them down on the ground. Now, obviously, that's a probably less stringent explanation of that observation, but that's what inference is. Now, there are several types of inference, and of course, who better to explain inference than Sherlock Holmes and Watson? So Watson is demonstrating the first type of inference. It's called a deduction. He's making two premises that are truthful. And so Sherlock is putting those together to come up with a third idea. And that is what is called deduction. If Moriarty is a criminal and criminals break the law, then Moriarty breaks the law. So that's a deduction. So that's also known as top-down logic. If your premises are true, since you're becoming more specific, then your conclusion must be true. The problem is if your premises aren't true, you can run into problems. For example, if you think that things denser than water sink in it, I can get behind that. And if you say rocks are denser than water, then you can deduce that rocks will sink in water. The only problem is, of course, that not all rocks are denser than water. And so you could have faulty deductions if your premises are not true. The second type of inference is called induction. And so here's an example of this. The sun rises in the east every day, so we can infer that it should rise tomorrow. So although Sherlock calls this a deduction, it's actually not a deduction. In fact, a lot of what Sherlock does is not deduction. That's actually an induction in this case. And so we're looking at a bottom-up logic. We're taking a bunch of data and reaching a conclusion. So you might drop a bunch of rocks, they all sink, and so you can induce that the next rock will sink, but that's not necessarily true. Unlike deduction, since you're going to a broader idea, you're going beyond the data, then you cannot guarantee that that conclusion will be truthful no matter how good your observations are. You could drop 20 million rocks, but that doesn't guarantee that the next one will sink. So induction often includes some statement of probability. What Sherlock is really known for is the third type of inference that I just learned a little bit more about, and that's called abduction. And so, Sherlock notices that, infers that Watson has been to the barber through coming up with a theory to match the observations of a clean cut hair and mustache. But that's actually not induction. That's abduction. That's looking at a conclusion and coming up with a hypothesis to match this. So it's not a kidnapping. Abduction is, again, an inference to the best explanation. So, for example, if we observe that a rock is actually floating on water, that's a weird situation, and we might want to come up with some explanation. And we have a theory that that rock is less dense than water, and that leads to an experimentation. All inference can lead to experimentation, but abduction is probably what you're most used to thinking about. So a lot of people consider this the cornerstone of science, the idea of coming up with things we don't understand and then coming up with the reasons why that happens. And that leads, of course, nicely to the scientific method. This is how we build our knowledge of science. You might have memorized it in 3 steps or 7 steps or 8 steps. Of course, scientists don't do it in a rigid lockstep pattern. It's not like they go to one room to hypothesize and another room to experiment. It's fluid and it's flexible and it's imaginative. But there are certain key traits that you're going to see all the time. You're going to have to recognize and state some kind of problem. Inside the laboratory, you're going to observe and collect data. Hopefully you're writing down your data in a laboratory notebook, but even if you're at home, you do this. There's some disequilibrium in your life. For example, if you hear a noise outside a window, you're observing that data and storing it in your head. And once you try to come up with a reason of what that noise is, you're moving on to hypothesis, you're moving on to inference. All right, so if you hear a noise outside the window, you might hypothesize that it's a cat. And that, of course, is a testable hypothesis because you can evaluate that scientifically. You can look out the window. And so that's what, it goes beyond just an educated guess. So don't just say educated guess. It's an educated guess or an explanation that can be evaluated scientifically. Not quite the same as a theory. We'll explain why in the next lesson. But the if-then statement still holds true here. And so, for example, if I study in chemistry, then I should be able to score higher on the test than the class average, and that's a testable statement. So you have to make sure, again, that they are testable. An example I like to use is you might make the deduction that if I'm alive and I feel pain, trees are alive, so you might deduce that trees feel pain. So you've made a deduction, but that's not a testable hypothesis because we have no way to measure tree pain. If we had a pain treeometer that we could plug into a tree and measure pain, well, obviously that becomes testable. We might not want to know that trees feel pain. That might change our lifestyles a little bit. But nonetheless, that makes it an experiment then. And of course, that's how you test our hypothesis, through experimentation. Obviously, you're going to study the results and come to one of 2 conclusions. Either it's matching things or it doesn't match. Don't give up. If it works out, you state your conclusions in a way that other people can evaluate. And if it doesn't work out, you revise your hypothesis and start all over again. And that's the cyclical nature of science. And we'll diagram that in the next lesson. But an important thing to understand that good science is reproducible. Somebody else must be able to do what you've done, or it doesn't mean much. So thanks for listening to the first lesson. Again, in the next lesson, we'll review the scientific method, and then we'll differentiate theories and laws and talk a little bit more about the nature of science. Thanks for listening, and have a great day.